Yeah, then I think, Partha, you don't need an introduction anymore. Everybody has seen you in action. The slides for lecture 3 is already on. I think this is set up as a meeting so that everybody has the right at any time to ask questions. But please, because it's an online meeting, just do it in a considerate way, not to disturb the speaker and not to disturb each other. And at the end of the lecture, we will have plenty of time to ask further question and discuss further points. Yeah. So Partha, thank you so much for being with us. We are very much looking forward to entanglement dynamics induced by classical gravitational waves. And please, over to you.
Yeah, thank you, Professor. So I think we can start. So today I'm going to discuss, in our last lecture, we have seen that the Newtonian gravitational theory can be formulated in a language of geometry. And after that, we have seen that Einstein's general theory of relativity, according to the Einstein, gravity is nothing but a geometry of space-time in presence of matter distribution. So now, today, our intention to discuss the observable effect of gravitational wave, classical gravitational wave, which already detected by LIGO interferometric observatory, and see what is the novel observation can be obtained from these classical gravitational waves when it interact with quantum mechanical detector. And I have already mentioned that in our first lecture that we need quantum mechanical model for the detector because the gravitational waves detected at the length scale, which is of the order of 10 to the power minus 18 meters. And we know that this is just below of the atomic scale, and that's in that scale we can't say that the position momentum of the detector uh, particle is just commute to each other. So we can't ignore the effect of Heisenberg uncertainty principle at that level. And on the other side, since the gravitational waves is a very weak frequency and the corresponding wavelength should be very large. So compared to the wavelength of the gravitational wave, the size of the detector can be considered as a microscopic object. So in that sense, we can treat the detector as a point particle with respect to the gravitational wave length scale. So now, before going to detail of the discussion regarding our main motivation, let me quickly highlight the some mathematical prerequisite for our further calculations or further demonstrations. So we have seen that when we study special theory of relativity, our time described in terms of flat Minkowski metric. Flat Minkowski metric, which is nothing but a diagonal matrix, 4x4 matrix, whose element is defined and this way. But if you consider the Einstein theory of relativity, general theory of relativity, we have seen that the space-time no longer be considered as a flat and it should have some curved nature. So therefore, in order to identify the curved space-time, we need a specific non-trivial metric apart from this flat metric, flat Minkowski metric. So this is the concept for a Riemannian spacetime. Riemannian spacetime means where we can start from the metric, then we can formulate the Christoffel connection and other geometrical object. So this is our formulation for the Einstein theory of general theory of relativity. We can start from our metric. Now, if we consider now ask the following question: what is the weak effect? Because the Einstein equations is very complicated. It's a nonlinear differential equations. So at least our aim is to solve this equation linearizedly. So for this purpose, we just consider the following question: what is the weak effect of gravitations over and above of the flat Minkowski spacetime? So regarding this question, we can introduce the non-trivial metric G mu nu, which is no longer be flat, but it can be viewed as a fluctuation of flat Minkowski metric with respect to, due to the additional perturbation. This H mu nu is the effect of weak effect of gravitation. So therefore, the gravitation, you can visualize the gravitation is nothing but a weak fluctuation over and above the flat Minkowski spacetime. Okay, so this is the standpoint which I want to take for the further discussion. So the magnitude of this correction over and above this flat Minkowski metric is taken to be very, very small due to the weakness of gravity. So this suggests that we can introduce this notion of G mu nu with a down index is called the covariant metric. So you can immediately define the contravariant component of the metric by satisfying this relationship, and which satisfy this following expression, and we need to introduce this minus sign. Okay, because without minus sign they will not satisfy these above orthonormality conditions. So this is the basic mathematical prerequisite. But in order to understand the physics apart from these mathematical techniques, suppose we consider, now the point is that we have already claimed the gravitational weak effect can be viewed as a perturbation over a flat space-time. But this perturbation effect, this H mu unique, whether it is a unique for every observer, because it is observer dependent physics. Now, the point is that suppose if you change your coordinate system by with respect to some arbitrary infinite small transformation. Okay, so if you change your coordinate system, so it is clearly indicate that if you assign to different observer which label by the coordinate system, one is old coordinate system is x mu, and new coordinate system is just x mu prime, which differ by this small parameter xi. Now, using this coordinate transformation, one can immediately observe that the metric tensor will transform covariantly, and the new form of the metric can be rewrite in this following fashion, where we can immediately observe that the old structure of the metric with fluctuation is completely changed, and with respect to these following corrections due to the coordinate transformation. So what is the point? The point is that the notion of this fluctuation is not invariant with respect to all observers. So in other words, the notion of this fluctuation over flat space time is no longer look like a same form under arbitrary coordinate transformation at infinite small level. Okay, so this remind us the situation for the gauge transformation for electrodynamics. Okay, so in the case of the gauge transformation, now the question, if we just write down this, our famous form of the gauge field A mu, I hope those who are familiar with this notion of gauge transformation, they can understand the situation. The A mu goes to A mu prime, which is A mu plus del mu psi. So it's the gauge parameter. So this is the gauge transformation, normal Abelian gauge transformations. But the point is that under this gauge transformation, this is not invariant under gauge transformation. This is a variant, gauge variant object. So therefore, what is gauge invariant object, which is physical observable? The gauge variant object is just F mu, which is defined as electromagnetic field tensor, which is very important to discuss regarding the discussion of electrodynamics. So this object is really gauge invariant object. So therefore, in the same situation, for the case of linearized gravitation, we need to ask the question, what is invariant object with respect to this coordinate transformation? Because this fluctuation is not unique. Every observer assign different fluctuation with respect to their coordinate system. Then what is how one can justify the physical situation? Now, the point is that apparently the form of metric perturbation depends on the choice of coordinate system. In other words, the metric perturbation are gauge dependent, quote unquote gauge dependent, and thus we may choose a suitable gauge to simplify the situation. So therefore, in other words, this transformation allow us to choose a particular gauge to simplify our situation, because there are many possibilities. So therefore, to simplify our situation, we can choose our convenient gauge. But as I already mentioned, we need to first identify the gauge invariant object, which is remains same with respect to all gauge transformation. Okay. So now, in order to search this gauge invariant object, let us first introduce the metric using this metric perturbation. So one can write down the Christoffel symbol or Christoffel connection with respect to this old h mu. And we have already mentioned that this is not also transformed as a tensor under coordinate transformation. So it is not a good object. So therefore, using this fact, one can also define the Riemann tensor, which is basically just defined in terms of this Christoffel connection. And if you explicitly write down the form of Christoffel connection using this metric perturbation, you will arrive at this structure. Okay. So in the intermediate step, we don't need to exactly show the intermediate step, because in this lecture, we want to understand what is the essential message we can understand from this discussion. So now, consequently, the Ricci tensor, one can also rewrite in this following fashion. So we have already mentioned this geometrical object in our second lecture. Now we can immediately observe this expression also can be rewritten in this simple form. Please note that this comma indicate this is indication of the derivative with respect to, I mean, this comma means this is a derivative with respect to del nu del alpha. Okay, so this comma is the indication of the derivative. Now the point is, we have already mentioned that the structure of the Riemann tensor, Ricci scalar, and Ricci tensor in terms of the metric perturbations or metric fluctuations. So with this result in hand, all of them are standard textbook result. Now, if we consider the Einstein gravitations equations, which is basically G mu nu. By the way, I need to mention one point. In our second lecture, I have made some mistake, because I have used this negative sign in front of this 8 pi g, but this sign should be positive. So I just want to make this correction in my slide. So now it is a correct form, written in the correct form. Now the point is that this Einstein's equation will take this following structure, where G mu nu just looks like this following expression, which is called the Einstein tensor. Now, it may be convenient to introduce the other object, which is called the trace reverse form of the metric perturbation, which is defined in this following fashion. What is the meaning of trace reverse? Because if you calculate the trace of h mu nu bar, it will be equal and opposite to the h. H means the original fluctuation h. But why we need to consider this kind of situation? Because we can immediately observe that the G mu nu can be written as a more simple form with respect to this new tensor H mu nu bar, which is a trace reverse tensor. And one can immediately observe that this G mu nu can be written in the more simplified form if we demand, because we have already mentioned that H mu nu is not a unique object, because it will be changed under coordinate transformation. Accordingly, this h mu nu bar also be changed under coordinate transformation. So therefore, we need to choose particular coordinate transformation, and this particular coordinate transformation can allow us to fix the following object, this h mu nu h mu alpha bar with respect to mu nu derivative is all of the derivative is fixed to be 0. These are ordinary partial derivative. So that is why I need to mention by comma. So therefore, if we just define or demand the derivative of h mu nu bar with respect to the alpha, that means this is the derivative with respect to del x mu alpha of this h mu alpha bar is 0. So demanding this condition, this Einstein tensor will take more simple form, which is basically box of h mu. This gets freedom, allow us to choose particular condition, because we know that this h is not the observable, because the observable is basically we can observe that the observable is this R. And we have already mentioned that the h mu nu bar also transform under coordinate transformation in this following way. So therefore, what is the observable or what is the gauge invariant object? The gauge invariant object is Riemann tensor. So which will take the same form with respect to any arbitrary coordinate transformation at infinite small level. So this is the observable. So since this coordinate transformation is remain invariant, I mean this Riemann tensor is remain invariant under such coordinate transformation. So this coordinate transformation can be fixed by this gauge choice. So this is our gauge fixing condition. It's called the similar to the Lorentz gauge for electrodynamic situation. Now, with this condition in hand, because you know that this condition cannot change the expression of this R mu nu because this object is gauge invariant. So therefore, if this Riemann tensor is gauge invariant, so you can choose any arbitrary gauge condition. So for particular situation, we choose this condition to simplify our Einstein equation. So this is the motivation. So we can introduce a particular coordinate system with this condition in hand so that Einstein equation looks like a very simple form. So you see there, this is the Einstein equation in a linear S level, which is not looking in a simple form. But with this condition, it looked like a very simple form. So this suggests us, this reminds us the situation you can interpret this equation with this gauge condition as a wave equation which driven by the source which is defined in terms of this energy momentum tensor T mu nu. This is a matter. So therefore, you can indicate that the origin of H mu nu is basically due to presence of matter density in the space-time. Okay. Now, but we can also simplify the situation furthermore. But because we wanted to, we are interested to study the effect of gravitational wave far from its source. So if we study the effect of gravitational wave far from its origin, then you can visualize the situation where the gravitational wave is affected. There are no matter distribution. So in that situation, we can consider the Einstein equation in absence of any matter, which is called the vacuum equation. So in presence of this, in absence of this, any source term or any matter energy momentum tensor or matter distribution, there are we can further choice our gauge fixing condition. We can introduce the additional constant which I already mentioned in our second lecture, which is basically known as transverse traceless gauge condition. So therefore, this is the analogous to the Coulomb gauge condition. In the context of electrodynamics, the first condition, this is basically analogous to the Lorentz gauge. Sometimes it is known as harmonic gauge in this context. I will refer for this discussion the textbook by Landau Lipschitz, Classical Theory of Field. Now, in absence of any source, we can further reduce your gauge condition and we impose additional gauge condition, which is basically a transversality condition, and this is basically the traceless condition. So therefore, we demand further the H mu is a traceless and all space-time component is 0. So we are focused only on the spatial component. So due to presence of this second term, this is called a transversality. This is the traceless condition. So imposing this additional condition over and above this previous condition, you arrive at this following structure. So therefore, this is your equations with this condition. But further imposing the condition, these equations become a more simple form because you demand that no energy momentum tensor, no source term, and this using this traceless condition, one can immediately observe that traceless condition demand that H mu nu bar is just equal to H mu nu, because if you demand H is 0, H is a trace part. So if you demand the metric perturbation is traceless, so therefore the H mu nu and the H mu nu bar, there are no difference, no mathematical difference. So you can replace H mu nu bar by H. So you arrive at this expression. And now this equation is just like a situation for the wave equation, Klein-Gordon wave equation or massless Klein-Gordon equations with different components. Now we can solve easily this equation, and since we have already mentioned that this h mu nu satisfy this condition, this is called the transversality condition. So we can immediately observe that suppose you immediately observe this Ajk is 0. This is the transversality condition. Okay. Now if we define Ajk just as epsilon jk, because the left hand side is a tensor, so right hand side should be tensor, some tensor which could be known as polarization tensor, times e to the power I omega gt minus k. Suppose you consider the gravitational wave propagate, for simple situation, propagate along z direction, so it is kz. So if you substitute this expression here, you immediately arrive at this will give rise to basically most general situation. I can say for general situation, say k dot r initially, say k dot r. So using this condition, you arrive at kj epsilon jk, which is 0. So when you substitute this equation, this conversality condition gives rise to this condition over this polarization tensor. And now if we choose the k is basically 0, 0, k, that means a vector pointed along z direction. Okay. Now if you consider such situation, so this suggests that k1 epsilon 1 2. So therefore this indicate that this one can immediately observe this with the choice, this epsilon jk can be considered as a 3 by 3 matrix. In general, it is 3 by 3 matrix whose diagonal term equal and opposite, because it should be traceless. Off diagonal term same, symmetric due to the symmetric condition. So you can immediately observe this is basically epsilon 1 1, epsilon 1 2, epsilon 1 3. So now you can immediately observe this condition can be satisfied by this choice of epsilon when you consider k propagating along z direction. Because if you consider the third component is non-trivial, to satisfy this condition, the third element, so 3 by 3 element, or the third element of this diagonal term, it should be 0. So therefore, you can focus only on the non-trivial block of this polarization tensor. So for this particular case, we will focus ourselves only this particular block of the 3 by 3 matrix. So now, with this situation, one can consider the particular form of the metric perturbation propagating along z direction with this structure. And since we are considering only the 2 by 2 block, this 2 by 2 block can be written in terms of this Pauli spin matrix, which is sigma 1 and sigma 3, which is already given in the reference book by Meissner Thornweiler. Now, the first term is chi naught, is nothing but the amplitude of the gravitational waves, and the rest of the part, sorry, can you hear me? Sorry, can you hear me properly? I think you can hear me. So the rest
Yes,
of the part
sir.
is basically, okay. So the rest of the part is basically the propagation part. Then the propagation part contains the space and time form. Now the interesting situation. Since we have the following cross and plus polarization. So what is the meaning of this cross and plus? I will demonstrate with this picture. Suppose you consider a planar system. Since we are focusing on a 2 by 2 block of this metric perturbation, which is basically a 2 by 2 matrix, basically H11. So basically it is H11, H12, H21, H22. Look like this. So therefore, this is the structure of Hij for this particular situation. Now, if you consider a plane x1 and x2 or xy, just consider a circle. And if you consider the some particles just arrange with the circumference of the circle. Okay. Initially, you consider this situation. Now, it is a situation before gravitational wave passing through this plane. Okay. Now, the direction of gravitational wave, suppose the direction of gravitational wave is basically z-axis. Now, when the gravitational wave passing through this plane, then the shape of this circular mass distribution or particle distribution over the circumference of the circle can be changed to the elliptical shape. So there are two possibilities. Two possibility means this circle can be deformed in the particular way, or it can be deformed in the particular way. So therefore, the relative distance or relative separation between two successive particles always change in a particular fashion. So therefore, we can demonstrate this fact by introducing this picture. Now you can immediately observe. Suppose you consider a bunch of test particles in a distributed over the circumference of a circle in an XY plane. Now, if you allow the gravitational wave passing through this plane, the relative positions of two successive particles change when the gravitational wave traveling along z directions and passes through them. Now, the circular system of particles can be deformed in this following fashion. You can immediately observe it will change to the circular form, change to the elliptical form, where the major axis sometimes major axis is aligned to the y direction, sometimes the major axis aligned to the x direction. Okay, these kind of variations. So this suggests that the gravitational wave only change the relative separation between relative separation among the particles. So when the gravitational wave passes through this kind of situation, we can observe some deformations of the shape of the particles distributions. Now, for the case of plus polarization, sorry, this is the case of plus polarization. For the case of cross polarization, one can observe the the circular shape of the particle distribution. Now the change to the elliptical shape with this following form of the ellipse. So now you can immediately observe this is correspond to the cross, because you can make some 45-degree line to join these two ellipses, and you can always define two perpendicular line to join these two ellipses, one kind of the prolate and oblate ellipse. So this is the indication that when gravitational wave passes through the planes with containing some mass distribution in a circular chain, then the shape of this chain always deform. So that situation also can be appear in the context of when you consider the LIGO detector. LIGO detector is just a two perpendicular arm, and when you consider perpendicular and gravitational wave passes through this region, then the arm length there is some deformation or distortion within the arm length due to presence of the gravitational waves. Now the question is, what is the physical estimation of this arm length, or physical observation or consequence of this distortion of the arm length? Or you can visualize this is the distortion or change of the relative separation of two particles which follow their own trajectory or geodesy. Now, so therefore, the neighboring test particle will be displaced from the circle according to the polarization of waves, as we have already demonstrated in the picture. Now, if incoming wave has the plus polarization, then the circle of particles will be distorted with time into ellipse of different eccentricities, whose major and minor axes lie along z, x, and y axis. Now, with this observation, this motivated us, in order to estimate any observational consequence due to the gravitational wave, we need to consider geodesic deviation equation instead of a single geodesic equation. Okay, because this is the practical demonstration, because the gravitational wave only can change the relative distance or relative separation between two particles. Now, in order to justify the situation more rigorous manner, we just consider the geodesic deviation equation, where this q is the relative. I mean, this is the q is the vector or separation vector corresponding to the adjacent particle geodesic x mu. Now, if you further consider that the gravitational wave has a long wavelength, and with this long wavelength approximation, the spatial part of the plane wave can be approximate to 1, because it will demand that the size of the particle is very small with respect to the wavelength of the gravitational wave. So therefore, compared to the gravitational wave, we can consider the detector is just a point-like object. It is not the point-like object with respect to us. It's a point-like object with respect to the gravitational wave length scale. So this is the comparison between the length scale. Okay. I'm not saying that LIGO detector is just a microscopic object. It is a macroscopic object with respect to our length scale. Okay. So now the point is that using this approximation, long wavelength approximation, and if we consider the particles is very slowly moving particles with respect, I mean, when the gravitational wave propagate along z direction, then the geodesic deviation equation can be approximate with this structure. Now the point is, the geodesic deviation equation is giving rise to this structure, and this will give rise to the forcing term if we just transform this r with this in terms of this h. So therefore, this forcing term basically introducing that when gravitational wave passes through this kind of bunch of particles, let us consider two particle system, then the relative separation will be changed due to presence of this force term. So you can visualize this is just a Newton's second law of motion. So this can be considered as two-dimensional motion of a particle influenced by gravitational wave relative to fixed reference point under the forcing term. The mechanical, now the question is, it is the situation when two particles only experience the gravitational effect. Now, if we go beyond and if you add some additional potential or additional force on this system, suppose you consider the system is basically placed in a, suppose consider a harmonic, a particle is connected by a spring and gravitational wave passes through the z direction. When the gravitational wave passes through the z directions, let us call this is the y. This is the y, so relative separation. When the gravitational wave passes through this, y will change due to presence of this force term due to the gravitational wave. But due to presence of this spring, the spring has the spring constant. So therefore, in that situation, the system also experience some additional force due to this harmonic interaction. Okay, so the first term can be considered as a geometric force, and the second term can be considered as a mechanical force or non-geometric term. Now we can observe that this equation, the geodesic equation with this forcing term, gravitational waves due to the gravitational wave and the mechanical, we can derive from the Euler-Lagrange equation of the corresponding Lagrangian. And the moment you have this Lagrangian, which enable us to can provide this equation of motion under the variation of this action with respect to this Lagrangian, the moment you have this Lagrangian, you can also define the Hamiltonian standard via the standard Legendre transformations. So therefore, this Hamiltonian is basically encode the information between the interaction between the particles with the gravitational wave. So since our aim to provide a quantum mechanical description of two particle model in terms of the geodesic motion, So the quantum mechanics based on the Hamiltonian formulation. So therefore, we need to define proper phase space variable or position and momentum. And also we can rewrite this expression under this approximation of linearized gravitational waves. We can rewrite this Hamiltonian, sorry, this should be the H in these two parts. One is the usual harmonic oscillator part and other is the interaction part. And this interaction is basically given by this following structure, which encode the information of classical gravitational wave. This overhead dot is basically the derivative with respect to time. Now, this QK and PK is a detector phase space chord variable. So therefore, there are three components. There are two components. One is the gravitational wave component, and other is the detector component, detector variable. Now, in order to study the quantum theory of this system, let us assume gravitational wave still classical, but the detector coordinate or detector phase space variable can be promoted at the level of operator valued object to incorporate the Heisenberg uncertainty principle at this level. Now, if we incorporate this Heisenberg uncertainty principle at this level, we can obtain this operator valued Hamiltonian, where the kinetic term and potential term already given in this the standard structure. But this additional interaction term due to the gravitational wave can be split into three terms. This second term is basically the presence of the plus polarization term. The third term also be the plus polarization term because we have two diagonal components, H11 and H22. So this is the first diagonal, this is the second diagonal, and this is correspond to the effect of off diagonal. So this expression of Hamiltonian tells us in the presence of gravitational wave interaction, this delta associated with the cross polarization, this cross polarization term always coupled to degrees the degrees of freedom of the system. So therefore, due to presence of this cross polarization term, the degrees of freedom of the system always couple to each other. But due to presence of the plus polarization term, the degrees of freedom of the system will not couple, they always separate. So the gravitational interactions separately interact with 2 degrees of freedom through the plus polarization. Gravitational interaction couple to degrees of freedom through the cross polarization. Now you can ask the following question. What is the meaning of this coupling? Does it indicate some physical indication? Answer is yes. Because if we consider the linearized gravitational wave using this following structure, as we have already mentioned, the sky at this long wavelength approximation is nothing but the periodic wave, or sorry, the periodic function over time due to the wave solution. Now, to understand this coupling, solely presence of this coupling, so now we can get rid of this second and third term by simple choice of canonical transformation. So if we just consider a new phase space variable by choosing our coordinate system and momentum variables by simple rotation, by this rotation enable us to rewrite the Hamiltonian. This is a time independent rotation because you can see this theta is basically defined in terms of the ratio of gamma and delta, and gamma and delta contain the same time dependent function. So therefore the ratio is time independent. So these are time independent canonical transformation. And under this canonical transformation, the system Hamiltonian boils down to this following structure. And you can immediately observe using this structure, you can align or you can completely get rid of the expression of plus polarization term, and it will look effectively the system influenced by the cross polarization term, where GT is the effective parameter which encode the information of delta and gamma. So now the systems look simple. It will contain the less term, and we will focus ourselves only this additional coupling term between two degrees of freedom. Now, we can also introduce, since it is a harmonic oscillator system, we can also introduce the ladder operator, the standard definition of ladder operator. And using this ladder operator, now we can rewrite this Hamiltonian in this following structure. So The first term is the standard kinetic term. Second term is nothing but the two-mode squeezing term. And this two-mode squeezing term basically gives some important result in our present discussion. I think these are all standard technique. Now, let us put some important observation. The two-dimensional system, in our case, now affected by the gravitational wave, and the modification in the Hamiltonian is done by a two-mode squeezing term. And considering this term as a perturbation, we expect that such a squeezing term will have very important effect on the quantum state of the unperturbed Hamiltonian. And we should note that it may be noted that the expression of chi gamma has some explicit time dependent structure. So this is the explicit form of chi delta gamma. Delta gamma is already appear at the level of Hamiltonian coupling term. So therefore, we have the all coupling parameter in terms of this gravitational wave in parameters, which is basically polarization tensor component and the frequency. So all of them are gravitational waves parameter. Now, in order to study the effect of, as we have already mentioned that we asked the question, what is the effect of this interaction, the squeezing term, two-mode squeezing term, over and above this unperturbed. So we can interpret our model as a time-dependent perturbation theory model. And initially, we can immediately observe G, T is depending on this following structure of time-dependent function, which is basically sine function. Now, at t equal to 0 initially, G is completely 0. So therefore, at t equal to 0, there are no gravitational interactions. So therefore, system is completely free from the gravitational wave interaction. So at t equal to 0, we can define our initial state, which is basically the ground state of two oscillators. 1 and 2 basically indicate that the ground state associated with ground state corresponding to the two modes of this oscillator. Because we have the two-dimensional oscillator, so therefore each mode provide us the ground state. So this is the explicit structure, which is basically initially you can write is a completely separable way. Now, since at t equal to 0, system is completely free, just a free harmonic oscillator, and we know that the eigenstate of the free harmonic oscillator provide a completeness relation. And this is the basically this is the expression of completeness relation of any Hermitian operator eigenstate provide the completeness relation because they satisfy the orthonormality conditions, and they can be treated as a basis of some Hilbert space. I assume some student is quite familiar with this notion. Now, this M1 and M2 at t equal to 0 can define also in this following factorized manner, which is basically 1 and 2 basically indicate the two independent mode of the oscillator state. Now the point is that since our system is now influenced by the gravitational interaction, so it is better to move on to the interaction picture. The basic motivation behind introducing the interaction picture is basically we want to study the evolution of the state. We want to study the time evolution of the state with respect to the interaction term of the Hamiltonian. And in this picture, the unperturbed term of the Hamiltonian is completely washed out. So that our system is just focused on we can focus ourselves only on the interaction term due to the gravitational effect. Now, this is the transformation from the Schrödinger state in Schrödinger picture to interaction picture. This is the basic definition of the state in the Schrödinger interaction picture. And in interaction picture, the Schrödinger equation looks like this following structure. Now you can immediately observe that this is the effective Schrödinger equation where the evolution of the state governed by the interaction Hamiltonian in interaction. So this is the beauty of interaction picture, because we don't need to bother about the unperturbed piece of the Hamiltonian. So unperturbed piece means I just want to focus this H this part, first term, this unpart of this. So in the interaction picture, we can only focus on this interaction term. So what is the physical effect of this interaction term? We just ask this question. Now, using this result, one can study some important phenomena. Now, in interaction picture, if we start by the ground state and study the time evolution of the state with respect to time, the state evolves through this time evolution operator. And this state which is evolved with respect to the time evolution operator, is basically given by this following expression. Now, T is the time order product, and this is the standard definition of the time evolution operator in interaction picture. As we have already mentioned, the evolution will only governed by the interaction term of the Hamiltonian in interaction picture. So now, if you start by this initial state, you can ask what is the final state? Final state will be this. Now, where this interaction Hamiltonian in interaction picture will take this following expression. So it is a very simple algebra. You can arrive at this following expression after some little steps. Now, we can observe that this final state at time t, so the ground state when evolve with respect to the interaction Hamiltonian, you will arrive at some final state. But this final state can be expanded in terms of unperturbed eigenstate of the Hamiltonian. So let me introduce some following expressions. Suppose you have initial state at t equal to 0, and under time evolution, you arrive at final state at time t. I think in our notation is basically psi. Okay. So let me introduce this psi. Psi 0, 0 at time t in interaction picture, which is basically u t0 acting on 0, 0 at time t equal to 0. So this is the initial state, this is the final state. Now, this final state under the time evolution of the ground state can be written as introducing some identity in this way. Now, this identity, one can introduce the completeness relation for the resolution of eigenstate of unpart of Hamiltonian, which is basically m1, m2 at t equal to 0, m1, m2 at t equal to 0, u 0, 0 at t equal to 0, m1, m2. Now we can immediately observe the structure. Now you can define the structure. Let us define the structure is, say it is just a D. Let us define this is a D, M1, M2, 0, 0 at time t times M1, M2 at 0. So this clearly indicates the final state can be expanded in terms of the unperturbed eigenstate of the system Hamiltonian. So this coefficient encode the information of this interaction term, this interaction of gravitational waves. So therefore, after some little algebra, one can identify the coefficient can be expressed in this following structure. So therefore, this coefficient in our calculation, we have seen that this d m1 m2 0, 0 at time t is proportional to some Kronecker m1 m2. So only diagonal term of this series will survive. So we have seen this following expression arise naturally. And after doing these steps, we can define the normalized final state in this following series expansion. So what is the meaning of this equation? This equation 97 indicate that the final state after the time evolution with respect to the gravitational interaction due to this interaction term of the Hamiltonian is no longer be factorizable in terms of the unpart of eigenstate of the system. So this indicates some important notion. This indicates somehow gravitational interaction entangled two modes of unpart of states in a particular way. And this entangled state can be identified in terms of, so this is the definition of A1, A2, which looks this complicated structure, and it is basically doing some approximation of gravitational interaction in the linearized level. Now, in order to identify the notion of entanglement to states, what is entanglement? Entanglement means in a simple language, we can say if you have two states, say gate 0 and gate 1, 1 comma 0 or 0 comma 1. So you can rewrite in the factorized manner. But if you consider the state 0 1 plus 1 0, which is basically with some root 2, you can't factorize this state in two different states. So therefore, this seems to indicate some entanglement or some intimate connection between two states via some interaction. So now, in order to identify or justify this situation, let us find out the density concept of density matrix for this final state. So since we study the time evolution of the ground state of system at time t equal to 0, which is basically unitary evolution, and after unitary evolution, any state boils down to the pure state. So therefore, we can define the pure state density matrix associated with the final state. Sorry, this capital T should be small t. This is a pure state density matrix because you can identify this concept of density matrix satisfy this condition, and this condition indicate that is a pure state. So of all density matrices, trace is 1. But trace, I mean the square of density matrix, if it is trace is 1, then it is a pure state. This is a hallmark of pure state. Now the point is that this final state encodes the information of both encode the information of the states of the two modes of the system oscillator. Now, if you want to focus only on mode, and if you just want to probe a single mode among these two modes, if you want to probe the single mode, then you can think you just forget about the information of the other mode. So this can be done by taking the tracing over the second mode. So if you want to focus on the first mode, then you can tracing over the second mode. It's called the partial trace. So your system is now a bipartite system. You can view in this way, the infinite dimensional bipartite system. Now your system composed in the two subsystem. Now you want to focus only one subsystem, and you just tracing over the remaining part of the other system. I mean, remaining part of this system, or you can just trace over the other subsystem. And after taking over this trace, you will arrive at the notion of reduced density matrix. And this reduced density matrix will take this following structure. And you can immediately observe this reduced density matrix is nothing but this is just a statistical mixture of pure state, or you can visualize it is nothing but a linear superposition of the pure state density matrix. So this reduced density matrix, the moment you have this reduced density matrix, one can define the notion of, because you already lose your information of the second subsystem. So this loss of information manifested in a language of entropy in this particular case. And this entropy in this context known as von Neumann entropy or entanglement entropy, we can define in this following fashion. And after taking this trace, now you can taking over the trace of this your probing system. You want to probe the first subsystem. So now you can take the trace over this first subsystem of the with respect to this reduced density matrix, and you will take, after taking this trace, you will arrive at this following expression, and after approximation with this linearized level, you will get this simple structure of the entropy. So the entropy controlled by this C mod square, C plus mod square parameter, which is time dependent. The first side, at a first side, this time dependent notion of entropy indicate that this is a dynamical nature. So therefore, the time dependent entropy, this is not it will change with respect to time. So this is why the notion of dynamics of entanglement arise. Now, so note that this entropy can be non-vanishing, and although it was zero at t equal to 0. So initially at t equal to 0, there are no gravitational interactions, so the entropy is 0. So this indicates that gravitational waves assist a quantum entanglement between two modes of oscillator, which was initially were not entangled. So now, in order to justify the notion of entanglement in a more simple language, one can introduce another degree of entanglement by introducing a purity function. So the purity function is just a simple trace over the reduced density matrix. Sorry, this rho 1 basically indication of this. We are considering the reduced density matrix and associated for the first subsystem. So therefore, after calculation, you can immediately observe this P is basically looks like this following structure. So again, C plus mod square. And the point is that is this purity function, if the purity function is 1 or unity, this indicate the state of this system completely decoupled or disentangled. There are no entanglement. But if this purity function departing from the unity, this indicate that the situation or the two state or two subsystem entangled with respect to this interaction. So therefore the degree of entanglement can be measured by simple calculation of the purity function of the system. Now one can immediately observe that this C plus mod square is the complicated form, because the C plus mod square is a central object which can control the purity function or entropy. So therefore you can decide which can be assigned as a degree of entanglement. For simple language, the purity function is the most simple. So therefore, any one of the case, the C plus mod square is a central object. So we need to calculate the C plus mod square, but which looks like complicated structure. Now, the C plus mod square involve two time scale. One is time scale associated by the gravitational waves, and other time scale associated by the frequency of system, normal mode frequency of the system oscillator. And F is nothing but the ratio between two frequency. So now we can see the following situation by graphical plot of this C plus mod square. Now we can define dimensionless object Y by rescaling the C plus mod square, and one can define the dimensionless amplitude of the gravitational wave interaction by defining Z. Now you can plot Z and Y in a same curve. This red color curve is basically this is the fluctuation of Y, which encode the C plus mod square, which is basically the key factor for entanglement generation. And this blue color is basically associated for the maximum intensity of incident gravitational waves. Now the point is that initially at time t equal to 0, so the x-axis associated for the time. So at time t equal to 0, initially there are no entanglement, there are no gravitational wave interaction. No gravitational wave interaction, no entanglement. So it is consistent. Now, when time is evolved, gravitational wave intensity increase with magnitude. Entanglement also generate because this entanglement will take some peak value when gravitational wave also take the peak value. But the moment gravitational waves intensity fall down, the notion of entanglement generated by Y, I mean encoding the C plus mod square, will also falling down. But when this gravitational wave intensity is completely zero at a particular time, this is because it is a periodic function, sinusoidal function. So it is a periodic ups and down of the amplitude. So when the gravitational wave intensity again zero at a particular time, you can immediately observe the entanglement generation of these two mode of the system oscillator is no longer zero. It will again show up some finite value. So you can interpret this as a residual part, or residual entanglement also can be observed in this system when the gravitational intensity is completely zero. So what is the meaning of this situation? This situation indicates that the moment the system is entangled in presence of gravitational waves, the notion of entanglement somehow trapped or memorized by the system, even if the gravitational wave intensity is completely zero at a particular moment. So this situation reminds us the situation for ferromagnetic system. If those who are familiar with this magnetism, you can visualize, suppose if you have the magnetization M and magnetic field B, now you know that when magnetic field applied, the system is magnetized, after some time is saturated. Now if you decrease the magnetic field and magnetic field goes to switch off, then but still system is magnetized. So this situation is similar to the situation when gravitational waves is completely intensity is completely zero, but still system is entangled. I'm not saying that two system is equivalent. I'm saying the situation is remind us this similar situation. Now, in order to cancel this magnetization, we need to apply the negative magnetic field. And you know that the negative magnetic field also, when you switch off, then again system is magnetized. So system always show up some residual magnetic field, or say residual magnetization, and this will give rise to the hysteresis. So the system somehow can memorize its past history even in absence of gravitational interaction. So this kind of situation we call is a quantum memory effect. And not only that, when you increase your time scale, you can immediately observe that the intensity when this maximum, then notion of entanglement also fall down and goes to almost zero. So this suggests that the depth of entanglement. So therefore, the notion of entanglement also satisfies some periodic fashion. So this kind of situation is known as sudden death of entanglement, and again revival of entanglement. So entanglement can completely collapse, and after again time evolution, it can be revived after some time evolution. So this kind of behavior is very familiar in the context of the quantum optics situation, which is known as the revival and collapse of entanglement situation, which can be obtained in the context of gravitational wave interaction. But the interpretation of the quantum memory effect is a very novel feature for this system. And this novel feature of this gravitational wave interaction induced only by the classical gravitational wave. So let us put some comments. The classical gravitational wave can help to provide the quantum communications, which in terms of the entanglement between two systems, and the entanglement persists even after the gravitational wave interaction is completely zero, and this situation is known as quantum memory effect. Entanglement exhibit dynamical fluctuation rising and falling with the peak of gravitational interaction. This is basically the situation for the revival and collapse of entanglement, which is basically the dynamical feature of entanglement. And this indicates some question. The question is, we have immediately observed the notion of entanglement only appear if we consider the off diagonal term of the interaction. So somehow we get rid of this diagonal term. Now, if we ask the reverse question, if you somehow get rid of this off diagonal term and persist the diagonal term, can you expect you can still have entanglement? In classical gravitational wave, we don't have any entanglement if we get rid of this off diagonal term and just persist of this diagonal. So diagonal term cannot create the entanglement, because in that level this plus polarization, basically diagonal term is the consequence of plus polarization, because this plus polarization basically introduce the interaction. So the gravitational wave interact individual modes of the system, not it will couple to the system. So therefore this diagonal term will be not define, will not create the entanglement. But if the gravitational wave, so therefore the classical gravitational wave for plus polarization, if we consider a particular polarized gravitational wave only have plus polarization, then this kind of plus polarized gravitational wave cannot show up any entanglement feature at the level of quantum detector. But if you believe the gravitational wave can be quantized, and if you believe the gravitational wave is quantized, then I will show you, then you can ask the question whether this quantized gravitational wave can produce the entanglement even if the classical situation there are no entanglement. So then this will be the hallmark. Then we can identify quantum and classical aspect of gravitational wave by their product. I mean, by their the notion of entanglement generation. So therefore, we can ask the question for our next lecture. The question is, can quantized gravitational wave with plus polarization create entanglement in a system where there are no coupling between two modes of oscillator at the classical level of gravitation? So I will discuss this context in the next lecture where I will introduce quantum notion of gravitation. So I think we can stop here. Thanks for your attention.
Yeah, thank you very much, Partha, for the very nice lecture again. Are there any questions or comments for Partha at this stage?
I would like to ask a question.
Please.
Yes.
So this is a very mathematical question that in the beginning of the talk, sir introduced us that we are allowed to take a Gauss transformation of H mu nu. So if I take that Gauss transformation, I don't remember the equation properly. If I take that Gauss transformation, will that necessarily affect my Hilbert space that the states are acting?
No, we introduced the quantum theory. Hilbert space of what? The system. Hilbert space of the system.
Yes, the
oscillator.
system.
Oh, but you see the notion of Hilbert space introduced only after the gauge fixing. So therefore, you can't ask the question what happened after gauge transformation because you already fix your gauge. There are no gauge freedom. You spoil your gauge symmetry by choosing a particular gauge. Do you follow?
Yes, yes. Now
the moment you fix your gauge condition, you don't have any gauge symmetry. So you can't ask the what happened after gauge transformation. So because we introduced the notion of Hilbert space of the system detector after the gauge fixing, which is basically transverse traceless gauge condition. So which can allow to disregard some spurious degrees of freedom of this gravitational wave interactions.
Okay, sir. Now I get it. Yes.
Okay. But the indication is that this situation is very similar to the electrodynamics, the Maxwell theory.
Yes, yes, yes.
Okay.
But here is the thing that this is from another thing or another topic, you can say, that we introduce the quantization by just saying that as my detector, which is now for consideration, I will say LIGO, is very small with respect to our gravitational waves that we are discussing or talking about. So for that reason, we can introduce them the things as the operator valued. But is this enough to say
no
about
this
the system's quantization?
This is not the only motivation for the this is the motivation why you consider your detector as a point object. You see, because we consider our particle is a point particle, there are no substructures. Okay, when you study the quantum mechanics, classical mechanics, we consider as a point particle mechanics because there are other mechanics which is called the field theory. I mean, classical field theory do not count any point like object. But the basic introduction behind the quantumness of the detector is basically when gravitational wave detected. Let me go back my first slide. We have seen that the deformation of the length. So let me just give me a few seconds. See, the deformation of the arm length of the LIGO detector is of the order of 10 to the power minus 18 meters. Okay.
Yes.
So this length scale is the indication that at that length scale, we can't avoid the notion of Heisenberg uncertainty principle. When the gravitational wave detected, of course, we avoid the Heisenberg uncertainty principle by saying that, okay, we can avoid some additional effect or noise effect, everything. We can avoid somehow. But if we allow to incorporate this effect, because this will be the important effect at this length scale, because it is a very, very tiny length scale, which is the just below to the atomic scale. So to capture, to see the effect of this length scale at this level of the detector, we just promoted our detector at the level of the quantum system. So this will be, you can visualize this is the advanced LIGO detector in the future.
Ah, I see. Now I can see. Okay. Thank you, sir.
I'm not saying the present detector is the quantum detector. You follow?
Yes, definitely. Okay, sir.
Okay.
Thank you, Partha, for the explanation. Are there further questions or comments for Partha? Partha, nobody seems to have questions, so your lecture was again very clear and pedagogically very well done. Thank you so much. That was a pleasure to listen. Yeah?
Thank you.
This was lecture number 3. And
Right,
there is no
it is 3.
There is no 3 without 4. Yeah. So please join us next week again for lecture number 4, which will be the last lecture in this series, in this mini school.
Okay.
And I'm sure that Partha will send me again the slides, and we will upload them on the website, so that maybe some of you that are not here today, that we've missed today, might have the opportunity to catch up also by watching the YouTube video, which hopefully by tomorrow should be uploaded as well. Yeah. So thank you very much, Partha, again for the nice lecture and for preparing it and delivering it so nicely. And thank you to the participants. Thank you very much. And I hope to see you all again next week. Same time, same Zoom link. Yeah. Thank you. Thank you very much.
Okay.
Have a good afternoon, everyone.
Okay.
Yeah. Thank you.